everyone. My name is Shreyansh Dikshit. In this presentation, I'll be discussing heat conduction in spherical coordinates, covering four key problems related to spherical systems and insulation. So, let's move ahead. In the first problem, we are given a hollow spherical shell transfers heat from a hot inner surface to a cooler outer environment. Heat flows radially outward through the shell from inner radius R1 to outer radius R2. Inner surface temperature is fixed at T1 and outer surface temperature is T2. System operates at a steady state, one-dimensional with constant thermal conductivity K. And we have to derive an expression for the radial heat transfer rate QR using Fourier's law and a differential energy balance. Okay. Uh, so in this question, basically it deals with the radial heat conduction through a hollow spherical shell. We are given inner and outer radii, along with temperatures at both surfaces. The system operates under steady state condition with one-dimensional radial heat flow and constant thermal conductivity. And okay, so we are moving on to the solution. The physical understanding basically. To understand this physically, imagine a hollow spherical shell which is hotter inside and cooler outside. Heat flows outward radially due to this temperature difference. Since the geometry is symmetric, temperature varies only with radius and not with angles. Also, because the system is in steady state, the heat entering equals the heat leaving. An important point here is that the area increases with radius, which affects how temperature changes. So, okay, this is all mentioned in this slide, whichever whatever I just talked about. And now we are moving on to the derivation part. So, in the step one is that we start with Fourier's law in spherical coordinates. That's QR equals to minus K into dt by dr. And then the step two, which is consider a thin spherical shell at radius r, whose area is 4 pi r square, the perpendicular area. And then the steady state energy balances. And then we take the limit and then we substitute the area and QR, which we defined earlier using Fourier's law into the above equation. And then we separate the variables and integrate from R1 to R2. And then we'll get a constant C, integration constant C, which by applying boundary conditions, the two boundary conditions will solve it. And then the final result will be something like this: Q equals to 4 pi K R1 into R2 into temperature difference divided by R2 minus R1. Okay. The final expression shows that the heat transfer depends on thermal conductivity, temperature difference, and the radii. We can also define thermal resistance similar to electrical resistance. The temperature profile is not linear. It follows a 1 by R variation that's hyperbolical. And this happens because the surface area increases as you move outwards. Okay. So here, the thermal resistance, which I've talked about, is R2 minus R1 divided by 4 pi K R1 R2. And this is the temperature profile equation. T minus T2 divided by T1 minus T2 equals 1 by R1 divided by R2, and which the as whole divided by 1 by R1 minus 1 by R2. So these are the relations we found for the first question. Now moving on to the next question. Okay. In this question, it's given a spherical metal ball of radius r is placed in an infinitely large volume of motionless fluid. Ball surface is maintained at a temperature Tr, fluid temperature far from the ball is T infinity, the ambient temperature. Since the fluid is completely stationary, heat only can leave ball by conduction through the fluid. We have to find the rate of heat transferred from the ball to the fluid, temperature distribution Tr, when the distance is greater than the radius of the metal ball. Then we have to find the Nusselt number also for this configuration. Okay, so let's move on to the solution, basically assumptions first. So the problem is similar to question one, but with the one key difference: the outer boundaries at infinity, which makes the case more easier, to be honest, because 1 by R2 equals 1 by infinity, and we know 1 by infinity is 0. So yeah, so the temperature approaches ambient as the radius increases infinitely. And also the temperature disturbance caused by the sphere is localized near its surface. So, which is all mentioned here. So, moving to the next slide. And now, the part A, the heat transfer rate. We just use the formula which we have derived in the first question and just put all the values. We get the heat transfer rate becomes proportional to the radius, thermal conductivity, and temperature difference. And also the temperature distribution follows a 1 by R relationship. Uh, this means the temperature drops rapidly as we move away from the sphere. So most of the heat transfer happens near the surface, which is all mentioned here. 1 by R decays faster than flat plate. The comparison is also shown here. So these are the results. Okay, moving on to the next slide. Now we need to calculate the Nusselt number. So by definition, we know that Nusselt number is average heat transfer coefficient into diameter divided by number coefficient K. And okay, from Newton's law of cooling, we have Q equals 4 pi R square into H into TR minus T infinity. And then we equate this Q, the conduction result, which we got earlier, as 4 pi RK into TR minus T infinity. And when we equate the above two, we get the relation of average heat transfer coefficient in terms of K and D. That's 2 KD. And when we put this relation in the Nusselt number, uh, we get the value of Nusselt number as 2. Now the physical significance, okay. Nusselt number equal to 2 is the absolute lower bound for the heat transfer from a sphere. Any fluid motion increases Nusselt number above 2. And an empirical relation is also shown here to just conclude the above things. And the value 2 arises directly from the spherical geometry, and the 1 by R temperature profile is not a coincidence. It's proved. Okay, so moving on to the next problem. Uh, Question number 3. A spherical tank has an inner radius R1 and outer radius R2, an insulating layer of variable outer radius R3. Inner fluid is at temperature TA with inner convection coefficient HA. Outer ambient is at TB with outer convection coefficient HB. Now we have to get how does the heat loss rate Q vary as insulation thickness increases. Also, one more thing, does adding more insulation always reduce heat loss from a curved surface? So this question focuses on a spherical tank with insulation. We are asked to study how heat loss changes as insulation thickness increases. Unlike flat surfaces, in spherical systems behave differently when insulation is added. Okay, so moving on to the next slide. We basically are going to approach this problem as we are solving a electrical series problem, basically four resistances in series. Uh, we model the system as a series of thermal resistances. These include inner convection, conduction through the wall, insulation resistance, and outer convection. So, defining all the four, firstly, we have inner convection, which is 1 by 4 pi R1 square into HA. And then steel conduction, R2 minus R1 divided by 4 pi KW, R1 minus R2, and insulation layer R3 minus R2 divided by 4 pi Ki R2 into R3. Similarly, for outer convection as well, we have 1 by 4 pi R3 square into HB. Now, uh, now the total will be the summation of all the four I have mentioned just before, and this is the total heat loss formula which is given. Okay, so moving on to the next slide. Okay, so effect one. These are the two competing effects here. First, adding insulation increases resistance, which reduces heat loss. Second, it increases surface area, which reduces convection resistance and increases heat loss. At a small thickness, the second effect dominates. So basically, in first one, more insulation, longer heat path. R insulation increases with R3, heat flow Q decreases. This is the desired effect. And for increased area one, we have got as R3 grows, outer area grows, and outer convection decreases, the outer convection resistance. So heat escapes more easily from outer surface. This is undesired. And yeah, now we are moving on to these are the key points, insights basically mentioned here. Now we are moving on to the next slide. So here we are calculating, so in this slide we are calculating critical radius of insulation. So for that, we have to let the x equals to denominator of Q, total thermal resistance. Then we just have to use basic algebra x dx. We have to minimize dx with x with respect to R3. It's dx by dr3 equals to 0. And by solving, we get the critical radius equals to ki divided by hb. And we just found the second derivative also to prove the above, which is positive. Therefore, x has a minimum here. So the physical meaning of critical radius depends only on insulation material and ambient convection. And this is the final formula of critical radius. Critical radius. Okay. Before this point, adding insulation increases heat loss, and after this point, insulation started reducing heat loss. This is the whole point of critical radius. So in this slide, we are calculating basically the equal loss radius. This is the insulation thickness at which Q exactly equals that of an uninsulated sphere. And the main point to note here is that R star, which is the equal loss radius, should always be greater than critical radius, and it should be much higher for large times. So yeah, I think this is for question number 3. Now we are moving on to the question number 4. So again, this is about insulation only. We have given a hollow steel sphere with inner radius and outer radius. Inner radius has a specific inner temperature. Outer radius has the a specific ambient temperature with the heat average coefficient. And then we have two insulating layers X and Y of 3 centimeter each. Material X thermal conductivity is given. Material Y's thermal conductivity is given. And a colleague claims the order of layers make no difference to heat loss rate Q. And we have to just check if he's right or wrong. Okay, so in this question, basically we have to check whether the order of insulation layers affects heat loss or not. We are given two materials with different conductivities and asked to compare the two arrangements. Okay, let's move forward to this. And okay, in this slide, basically, we have just written the given things. The spherical shell conduction resistance R shell equals to R out minus R in divided by K into R in into R out. Then outer convection resistance R con equals to 1 by R out square into H. Now we have the fixed resistance R steel and fixed resistance R convection also. So yeah, these are the two main formulas used here. Now we are moving on to the main part, which is the cases. In case 1, material X is inside and material Y is outside. And in case 2, the order is reversed. Y is inside and X is outside. So, okay, starting with case 1, uh, first we found out the total total resistance. Like first we found out Rx and Ry, and then adding everything, we get total resistance. Also, we have added that R steel and R convection, which I found out earlier. And then we get the heat loss, which is 91.6 watt here. And then for case 2, similarly, we found out total resistance is 19.43 and Q equals 103.5 watt. So clearly the difference is 11.9 watts, 13% more in case 2. Uh, so it shows that the order of insulation layer does matter and significantly matters. So placing the better insulating material closer to the inner surface minimizes the heat loss. This is an important design principle in spherical and cylindrical systems both. As we've observed in case 2, polar insulator Y sits at the inner position, wasting the geometric advantage, resulting in 13% more heat loss. So the basic engineering rule is place the material with lowest K at the innermost position to maximize its resistance contribution. Okay, I think we are done with this. This is the final slide. Yeah, the friend's claim is incorrect. The order of insulation. So yeah. Okay. Thank you.